Okay. Different. All right, we have R1, we have R2, and we have C. We have VS. VS, we're just going to make that equal to 20 volts. Why not switch it up? R1, we're going to make this equal to 1,000 ohms. R2, we're going to make this equal to 500 ohms. Why not? And C, we're going to make this equal to 0.1 millifarads, or I should say 100 microfarads. Okay? All right. What is step 1 of our solution? Draw a circuit. We've already done that, except for I didn't put the nodes in. Node 1, node 2, node 3. We'll go ahead and ground that one. Okay? So step 2 is build 3 equation sets. What are our 3 equation sets? And the component equations. What is KVL? How many loops do we have? We have 2 loops, which means we should have 2 equations. What are those 2 equations?
R1 and R2.
So here we've got VS equals VR1 plus VR2. There's 1, that's loop 1. And then for loop 2, what is the equation? Sure, why not throw a 1 on there? Okay, and we could actually have a third loop that goes here, and all that's going to say is that in loop 3, VR1 is equal to VC1, oh, VR2, which we can derive from the other 2 equations. All right, that's equation set number 1. What's equation set number 2? It's KCL. According to KCL, how many different nodes do we have? We have 3, which means we'll have 3 different equations. What is the KCL equation at number 1? Input equals output. We're bringing in current, we're bringing out current, node 1. What about at node 2? Yep. What about at 3?
IR2 plus IC1.
That's IS. But yes, you were right. There you go, 3 equations. That's equation set number 2. What is equation set number 3? What? It's component equations. What components do we have? Every one of them is going to have an equation, except for the power source. Somebody name a component. R1. Okay, so for R1, first, what was the relationship between voltage and current in R1? What kind of component is R1? It's part of the resistance. What's the relationship between voltage and current in a resistor? This is where you got to bring your ohms in. V1, VR1 is equal to IR1, R1. It's Ohm's law. Okay, what's the next component? R2. Just knock them down. What's the relationship between voltage and current in R2? What kind of component is R2? It's a resistor. What's the relationship between voltage and current in a resistor? It's Ohm's law again. VR2 is equal to IR2 times R2. Okay? What's our last component? C1. Now C1 is a capacitor. What's the relationship between voltage and current in a capacitor? It's one of those many equations that I handed you and said this is probably going to be really important in this class. We just used it in the last problem too. Yep. The current going through C1 is equal to C1 times dVC1 dt. That's the relationship between current and voltage in a capacitor. So we now have equation set 1, equation set 2, equation set 3. What is step 3, Trace?
Step 3 after this one?
Yep, we got the equation sets. What's step 3?
Find time or find final solution.
Find your final solution. Oh, dang. That one was actually supposed to be derive the equation. Oops. Because it was supposed to be that. What happens when you memorize your notes? We have to derive the equation. So, which equation are we going to start with? Let's say we're trying to solve for VC1. Which equation should we start with? You got 9 options. This one? We could start with that one. Why do you think this one?
Because then we only have, the next step will be really easy because we have to plug into the other thing.
We could solve VR2 with this one, yeah. But if we do that, then we'll get this equation. So, yes. But I'm going to give you a caveat of let's just start with that one. Make it a little bit easier on ourselves. The reason why I want to start with this one is because it's got something we know, which is Vs, and it's got what we want to know, which is Vc. Okay? So we start with this equation. Now we have to turn this equation into something that only consists of Vc1, which was supposed to be the step 3 in what I gave you. I thought there were supposed to be 7 steps. friggin' kale. Okay, what equations do we have that use VR1? We have the KVL equations, but if we just use those, we'll just derive a different one of these. So we really can't use KVL right now. What other equations do we have that use VR1? Yeah, we have a component equation. So that's the only other equation we have that uses VR1. I said don't use KVL because we'll just end up deriving another equation, which is true. If you plug in this equation into it, you end up getting this out of it, and that doesn't help us because then we're just running in circles. So you can't use KVL if you bring out a KVL equation because that's how you derive other KVL equations. Similarly, you can't do it with KCL either. If you start with a KCL equation, your next equation won't be KCL because it'll just be switching between these. All of these are derivations of each other. But regardless. So the next one is going to be, and almost always is, a component equation. Okay? So next step, component equation. We're going to go ahead and take Vs is equal to IR1 R1 plus VC1. Okay, what equations do we have that use IR1? There are, I think, 3 on the board. We have this one. Why'd you pick that one?
Because IC is related to VC.
It's the one that, I mean, it's got this one that we want, and it's got this one that we need, right? That makes sense. The problem is we got this IR2, but I guess we'll deal with that later. So IR1 is equal to IR2 plus IC1 times R1 plus VC1. Okay, now we've got the IC1. This one we can change directly into VC1 using the component equation. Okay, but what do we do with IR2? What other equations do we have that use IR2 that are not KCL? We have the component equation. You know what? Let's go ahead and try plugging that in. Vs is equal to IR2. If we solve for IR2, it would be equal to VR2 over R2 plus, and then I'm going to go ahead and I'm also going to plug in this for IC1. C1 dVC1 dt R1 plus VC1. Okay, now we have a VR2 in there. Do we have any equations that can help us out now? Huh? Yeah, that gets us right to where we want to be. So if we just plug that one in, this equation right here, then what we end up with is Vs is equal to Vc1 over R2 plus C1 dVc1 dt times R1 plus Vc1. And now we only have one variable in our equation, and that's VC1. This is our solution. This is just super gross. So let's clean this up a little bit. Okay, here, this is a VC1. Here, this is a VC1. So this is VC1 times, oh, I guess I'll just bring it out. This is R1 over R2, VC1 plus this is R1 C1 dVC1 dt plus VC1. All I did was I just multiplied the R1 through. And then we can add these two together, and we end up with Vs is equal to R1 over R2 plus 1 times VC1 plus R1 C1 dVC1 dt. And this is our constitutive equation. That one is the big kahuna laguna. Okay, what is our next step now? This is where.
Now it's find time function.
Now let's find the time function, okay? What we did to find the time function before was we solved the homogeneous equation. Well, actually I guess, first of all, before anything, the time function of VC1 is going to be equal to A1 e to the st. Oh, dang, no, sorry. VC1c plus VC1p. VC1c, we're going to guess, is A1 e to the st. And VC1p, we're going to guess, is A2. Why? Because this is a first order system. Okay, so now we need to solve for what S is. And to do so, we use the homogeneous equation. We plug this in, we set Vs equal to 0. So, the homogeneous equation, it's a tornado. Quick, everyone run. If we plug in our homogeneous equation, it's just this, where we're going to plug in our complementary solution. 0 is equal to R1 over R2 plus 1 times VC1 comma C plus R1 C1 d VC1 C dt. Okay, so then I'll actually write out what VC1C is. 0 equals R1 over R2 plus 1 times A1 e to the st plus R1 C1 A1, d dt of A1 e to the st. What is the derivative of A1 e to the st? You just throw an s out front. So this becomes 0 is equal to R1 over R2 plus 1 A1 e to the st plus R1 C1, I'm going to throw an s out front, times A1 e to the st. Okay, we can divide both sides by A1 e to the st. I'm going to rotate my camera. Ignore me for a little bit, Dylan. If we divide both sides by A1 e to the st, we get 0 is equal to R1 over R2 plus 1 plus R1 C1 S. And if you solve for S, which at this point everything is a constant, S is going to be equal to negative R1 over R2 plus 1 divided by R1 C1. You'll notice that the units on top are 1. The units on bottom are resistance multiplied by capacitance. That is the same as we had for the last time. So if we look at what the time constant is, tau, tau is just the negative inverse of this. So tau is going to be R1 C1 over R1 over R2 plus 1. Or you can rearrange this and make it a little prettier if you don't like having this, and it ends up being R1 R2 C1 over R1 plus R2. Samesies, just a little cleaner. Here, if you remember correctly, if we want this thing to take longer, we increase the value of tau. To increase the value of tau, you can see that, oh man, well, if you increase the capacitance, that's good. But you got this issue where you got the R1 and R2 on bottom. If either R1 or R2 are very small values, this thing is going to charge pretty quickly. If the fastest this can charge is if R1 and R2 are the same value, because that actually ends up, it's an optimization function. It's the largest value that's possible. But just playing around with math at that point. Okay, so we solve for S. Now we use the non-homogeneous equation, which should be what I gave you as what, step 5? If we use the non-homogeneous equation and we plug in the particular solution. Okay, again, remember, VC1 is equal to VC1C plus VC1P. We already know what VC1P is, our guess is. It's the same time function as our solution. So if we just go back into the original equation, Vs is equal to R1 over R2 plus 1 times VC1P plus R1C1 times the derivative of VC1P. That's our next step. What is VC1P? What is it? It's A2. It's a constant. So we'll just plug in A2 into this. So Vs is equal to R1 over R2 plus 1 times A2 plus R1C1 times the derivative of A2. What is the derivative of A2? It's 0. Like how Caden's over there in the background, like, I can't see anything. My apologies, man. Yeah. Problem is that right over in that corner, these guys need binoculars. Right over in this corner, you need binoculars. I just have to pick who I like more, really. Nice. Pocket spyglass. This equals to 0, which means what we're left with is Vs is equal to R1 over R2 plus 1 times A2. Which if we solve for A2, that means A2 is equal to Vs divided by R1 over R2 plus 1. Or you can simplify it a little bit if you really want. It's equal to Vs R2 divided by R1 plus R2. Both of those are equivalent. I don't care how you hand it into me. Just as long as it makes sense to you, and as long as it's right, I don't care what form you use. Jacob has died. Let's all go to his funeral now. Man was mathed to the death. All right, the next step. We've now solved the non-homogeneous equation. What is the last step? We use the initial conditions. Here, once again, I didn't give you the initial conditions. So let's assume that it starts with the voltage on the capacitor equal to 0. Why? Because that's easiest. And I'm tired. And I didn't give you guys 2 breaks, so I'm trying to finish this early. Okay, so. What's the first thing we write when we put down the initial conditions? What was the first equation we wrote last time? What? Right. So, assuming that at time 0, the voltage on the capacitor is 0, what's the second equation I gave you? So this is the initial condition that would be given to you by the problem. What is the next equation? It's already up on the board, but I just bring back one from our far distant history. We go back to this one. What is this equation? Why is this important? It's the end solution. It has both equations in it, but this is what we're trying to build towards. It's the whole reason why we were solving S. It has everything in it. Yes, you're both right. But it's our end solution. Okay? So right now we're trying to solve for our end solution. You plug in your end solution to the initial equations. For the non-homogeneous, what we plugged in was our constitutive equation. For the homogeneous equation, what we plugged in was our constitutive equation. For our initial conditions, we plug in the final solution. And we say, I know what the final solution is at some time t, therefore, I should be able to solve everything else that's left in the problem. Or at least get some kind of a relationship or something. So we just plug in final solution. VC1 is equal to VC1C plus VC1P. Particular plus complementary. Okay, we know that this value at t equals 0 is equal to 0. We know VC1C is equal to A1 e to the st. That's what we wrote right here. We know VC1P is equal to A2. I'm going to go ahead and write those in here now too. So VC1 is equal to A1 e to the st plus A2. It's just how it's complementary plus particular. Okay? Now we've already solved for which of these values? Which of these values do we know? Do we know what E is?
2.71.
It's not exact, but yes. That's given, it's a constant. Sorry, that was me being a jerk. You're a good sport. But yes, it's about 2.71. Do we know what S is? Yep. Do we know what T is? I mean, at this one, we're given that T equals 0. So at T equals 0, the function is equal to 0. So yeah, I mean, T is our independent variable there. Do we know what A2 is?
Yeah.
Yep, we just solved that. Do we know what VC1 is? At T equals 0. Do we know what VC1 is at T equals 0? Dylan says yes. It's right here. It's VC1 at T equals 0 equals 0. So we know this one. We don't know that one. We know this one. We know that one. We know that one. And we know this one. The only one that we don't know is A1. Which means plugging this into the final solution should give us the ability to solve for what A1 is. So we'll go ahead and plug in 0 for VC1. I'm going to choke on my own spit here, which is awesome. A1e to the s times 0 plus A2. When we plug in 0, what is e to the 0? It's 1. So this is 0 is equal to A1 plus A2, which means A1 is equal to negative A2. If we write out the final solution there, I'll make sure I'm still on camera, mostly. If we write out the final solution is VC1 is equal to, A1 is equal to negative A2, which is equal to negative VS R2 over R1 plus R2 times e to the s is equal to negative R1 plus R2 times T divided by R1, R2, C1 plus VS R2 over R1 plus R2. And that's our final solution. Same method, a little bit more geometry, a lot less fun. But I didn't use the whole board this time. Is this understandable? Okay, I would advise you to spend some time looking over your notes before Thursday, because this probably won't make sense on Thursday when we come back and do it again. Okay, here's the thing. It doesn't get easier from here. It gets harder, or stays about the same. So, review your notes. This is a hard class. There are very, very few people in the world that can do this, okay? If you struggle with this, it's normal. That's called being normal. It's okay to be normal. You don't get to be normal though. I don't know why, but you come in here like, I know everything, like, you jerk. Why am I even teaching you? Get up here and you teach. This is something where it's okay to struggle. It's okay if this doesn't make a whole lot of sense and you just kind of follow the procedure I gave you. It's okay if you just go through exactly what I did. Yes,
Is that a T or addition?
that's a T.
No, the next one.
That's an addition.
Okay.
It's okay if this doesn't make a lot of sense, okay? It's okay if you just kind of flying by the seat of your pants and trying to figure this out. You will notice, I mean, just looking at this, if we look at unit analysis on this, this is the voltage times the resistance divided by a resistance, which is going to have units of voltage. That's what you would expect. This year has units. I mean, it's got a resistance on top, it's got two resistances and a capacitance on bottom. It's got units of time divided by resistance times capacitance, which actually is unitless. Time divided by resistance times capacitance is nothing. This over here is a voltage times a resistance divided by a resistance, which is just units of voltage. So our unit analysis comes out just generally. If you plot that, you get what you end up with is the absolute largest value you can possibly get is Vs R2 divided by R1 plus R2. Vs times 500 divided by 1500, which is 1/3 of Vs, which means the maximum value of C1 is about 6 volts. Okay? And what this is going to do is this is how it reaches that 6 volts. It's the same exact shape for an equation. You want to plug that into your calculator, that's what you get. Okay, different numbers, a little bit more complex numbers, but it's the same shape. This is VC with time. Here, something that's interesting to note, VR2 with T has the exact same shape. Why? And it's always got the same voltage as VC. With all times T, VR2 is equal to VC1. So this is always, these are going to be identical. You can lay these on top of each other. They're not even scalar differences. These are identical values. Okay? But that also means that VR1 is going to be equal to Vs minus Vc1, which means that VR1 is going to be like this, where its final value, it starts at 20, it ends at 14 or 13. That's what VR1 looks like. Okay, any additional questions on this? All right, I will see you on Thursday. You have a homework assignment, you have a reading assignment, and you have a quiz due tonight. Good luck. Be sure to ask questions, because again, this is friggin' hard stuff. We're not playing with Duplos anymore. We're deriving high order equations.